Okay, so hello, good morning, everybody. Welcome to our third lecture.
Good morning, sir.
Good morning, Anjali. So we will continue talking about Minkowski space-time and space-time geometry. Okay, right. So in the previous two lectures, what I have done is I have introduced the concept of four-dimensional vectors, right? And then I've talked about this Einstein notation, summation notation, and I mentioned that this Minkowski metric tensor is used for raising and lowering indices. And then I explained the concept of contracting repeated indices, right? That's the summation convention. So I guess first two lectures have been all about that only. And then we talked about this, the norm of a four vector and how it is different from the norm of spatial vectors. So it can have null values and it can also be negative. And then I started talking about space-time diagrams and the fact that if you have a null vector, it corresponds to a light ray in space-time. If you have a space-like vector, it tells you that the 2 points are causally disconnected. And if you have a time-like vector, it tells you that 2 points are causally connected. So all this, of course, is a consequence of the postulates of special relativity, right? And so let's just remind ourselves what those two postulates are, right? The first one being that the laws of physics are the same for all inertial observers. And the second one being that the speed of light is the same for all observers. And it doesn't matter whether the observers are inertial or non-inertial, the speed of light is the same for all observers. So as a consequence of these two requirements, what the result is that if you want to ask how do coordinates transform from one frame of reference to another frame, you have to use the Lorentz transformation. So you have the Lorentz transformation is the following. And right, and this factor gamma, this is called the Lorentz factor. Now, this transformation connects coordinates in one frame of reference to those in a different frame of reference, moving with respect to the first frame of reference with some velocity v in the x direction, right? So if you, for instance, say that you have some observer O whose coordinates are x, in, let's say CT like this, and then you have some other observer O prime, right? And O prime is moving with some velocity v naught, and we assume that the x-axis of both of the observers are aligned for simplicity, right? Then and you look at single any point in space-time, right? Now the thing is that when we what are observers? An observer, a frame of reference is basically like a window to reality, to whatever there is around us, right? So you have you can sort of think of this whole setup with observers and so on as, let's say that you have a big castle, and in the castle you have people, right, in different chambers, okay, and so they all have each person in has a different view of the outside world, right? So this person has a view of the outside world as seen through this perspective, and this person sees the view of the outside world as seen from this perspective, right? So if you have like some object or anything out here, right? There's like let's say there's a beautiful lady standing out here, right? And these two are looking at this person from their own perspectives, right? And so this person will assign some set of coordinates, right, to this whatever they're looking at, right? So this person is O and this person is O prime. So O will say, oh, okay, this lady is standing at the position X and at the time T as measured by my watch, right? And O prime will say, well, the lady is standing at C X prime as measured by my coordinates, and the time is T prime as seen by my watch, right? So that's what this, so they are both looking at some event in space-time, right? And this event is independent of both of those observers. This is important to keep in mind, because sometimes it might seem like the event is embedded within the frame of reference, but it's not. It's like something independent of any observer, right? So the O prime says that the location of this lady is at X prime CT prime, and O says that no, the location of this lady is at X and CT prime, X and CT, right? And but these coordinates, they are related to each other by this transformation, right? And this transformation is a consequence of the first two postulates of relativity, right? So yes, Anand, you can just ask a question. You don't need to raise your hand or anything.
Sir, shouldn't x dash be the first equation?
Sorry, Anand, your voice is breaking up. I don't know what.
Hello?
Clearly, could you repeat?
Yeah. Sir, shouldn't x dash be the first equation and t dash be the second equation?
Thank you. When you're teaching the same thing over and over to BTech students and MSc students, you kind of tend to make. So this is X prime and this T prime, right? And now again, so I won't be deriving the Lorentz transformation and things, okay? Now, what about this this transformation? We can write it in a slightly more transparent way by using by defining a quantity beta, right? So this is a dimensionless quantity because these are both dimensions of the speed. So beta is dimensionless, right? And then we already have gamma, right? So if you look at these two expressions, the first expression, let's say x is equal to x minus v naught t by gamma, right? And we write this as v naught by c, right? Then the other term has to be written as c times t. So this becomes x minus beta. This becomes gamma x minus beta gamma ct, right? Because this quantity is beta. Similarly, for t prime, we do the same thing. We multiply t prime by c and t by c. And then over here, so we multiply everything by c. So here we get ct prime, here we get ct, and here we are left with v by c, which is beta, right? And the whole thing multiplied by gamma. So this becomes gamma times ct minus beta gamma x. Right? And now conventionally, what is done in most textbooks is that you set c is equal to 1. Okay, and we can always do that. And please mute yourself unless you want to ask a question. Okay. You can always do this. You can always set c is equal to 1. So if you do this, then we just get the following set of equations: x prime is equal to gamma x minus beta gamma t, and t prime is equal to minus beta gamma x plus gamma t. And now these equations can be written as a linear. This is a linear transformation of my coordinates, right? So this is a matrix. These are my coordinates. This is a vector containing the coordinates, and this is a matrix, right? But now we know that if you have a arbitrary point in space-time, it's actually represented by 4 coordinates rather than 3 coordinates, right? And again, from now on, I'm always assuming that c is equal to 1. Okay, when we need to do some calculations, we will insert factors of c in the appropriate places. So wherever you see time, for instance, you would have to multiply that time by c. So this is a space-time point, right? It has 4 coordinates. We have only looked at the transformation of these 2 coordinates. And that's fine, because right now we have made the assumption that what do you call it? The 2 x-axes are aligned, and the relative motion is along in the x-axis. Please keep yourself muted unless you want to ask a question. I won't mention this again. If you cannot do that, then I will have to mute everybody, and you will not be able to unmute yourself unless I am. Okay. Thank you. So the same point as seen by the other moving observer, right, will be some x mu prime, t prime, x prime, y prime, and z prime, right? And so the full Lorentz transformation is the 2 equations for x and t, but also the remaining two equations for y and z, which is that these are just equal, right? So if I want to write down the full transformation, how do I do that? Well, I write this as a 4 vector, and the components of the 4 vector as follows. right? So this is the full Lorentz transformation. But this is for a sort of a special case when the two x-axes are aligned. Later, we will see what the transformation looks like in general, okay? When there is no such alignment. So you can have an arbitrary velocity in any direction. Then we'll see what happens. So, right, and here, so only the tx components are non-zero. All the other components are either zero or identity. So y prime and z prime are the same as y and z. Now, this I write as x mu, right? And this, well, instead of writing it as x mu prime, I'll write it as x prime mu. Okay, I'll put the prime on the x instead of on the mu. So this will become, but then this is one of the most difficult questions in physics. Where should you put the prime? And I don't think there is a satisfactory answer to this question yet. So I'll put the prime on the mu again. So this is a mu and this is mu prime. And so this is a matrix, is a 2 by 2 matrix, right? So I'll write this as lambda. And this lambda will have two indices, right? What are those two indices? One index has to be mu prime for this guy, and one index has to be mu for this guy, right? And note the way in which I'm writing these indices. This is very important. So if you have any matrix, right? Now remember, there are 4 possible slots for the indices. There are 2 slots on top for if your index is raised, and 2 possible slots if your index is lowered, right? And only 2 of those slots can be filled at any one time, right? So you can have, for instance, the first index might be raised, in which case I would write something like this, mu. And the second index could be lowered. So where do I put the second index? I put it in this slot. So I leave a gap over here between mu and nu. This is important. So this is not the same as a mu nu. If you write it like this, then there is no way to tell which is the first index and which is the second index. And in general, right, if you are given some matrix, it might not be symmetric. That means if you switch the indices, the order of the indices, you might not get the same matrix element, right? So if you don't keep this order into account, you will be making a mistake. So this is important. So what is this lambda mu nu? Lambda mu nu, we have the first index over here. I'm drawing these boxes for convenience so that you can see how to write it, but now just visually you can leave a gap. Alternatively, we will also see something like this later, with the first index lower than the second index raised, right? Or you could have lambda mu prime mu or lambda mu prime. These are all different possibilities. But in this case and this case, you don't have to worry about spacing. It's kind of automatic. But here the spacing is important, okay? This space. All right. So now what do we have? We have x mu prime is equal to lambda mu prime mu, x mu. And again, we are using the summation convention. Which index is repeated? Mu. So this is a sum over mu is equal to, and what are the values of mu? From 0 to 3. And once again, I'll put this in I'll make this light, I'll make this gray just to indicate that, well, we kind of ignore this fact. So this transformation, this matrix, right, is our Lorentz transformation matrix. Okay, so these are 4 vectors and this is a matrix. Now, as I explained, for 3-dimensional vectors, for instance, you don't need to worry about upper indices and lower indices, right? Because there is no change when you raise or lower indices. So again, just to show you once more. So if you have a 3-dimensional vector and you raise or lower the indices, the components remain exactly the same, nothing changes, because you are raising or lowering using the metric in the 3-dimensional metric, right? And the 3-dimensional metric is what? It's just delta ij. And in the 4-dimensional case, when you raise and lower, what happens is that the sign of your time-like component gets changed, right? So if you write, where is it? If you write x mu with the index lowered as this 0, 1, 2, 3, right? Or if you like, you can just call them A, B, C, D. Then when you raise the index, what do you get? You get minus A, B, C. Okay. So for Lorentz vectors and 4-dimensional spacetime vectors, the index location is important. But if I have for instance, if I look at a rotation in 3 dimensions, right, in 3 spatial dimensions, how would I write that? I would say that a vector V has some components, let's say I prime. And now again, like I don't need to distinguish between upper and down. So I'll just use all lower indices and I'll write it like this. Where what is this? This is my rotation matrix. Right? And these are my 2 vectors, before and after rotation. Index level is not relevant. Okay. Okay. So this is a Lorentz transformation, but a Lorentz transformation is so what is this? This is a coordinate transformation. So what is a coordinate transformation? A coordinate transformation is just any function is some set of new coordinates which are functions of the old coordinates, right? As an example of a coordinate transformation, you can consider, for instance, going from Cartesian coordinates to polar coordinates, or from Cartesian coordinates in 3 dimensions to spherical coordinates in 3 dimensions, or to cylindrical coordinates in 3 dimensions. These are all examples of coordinate transformations, right? So, but these transformations are not necessarily linear. These are not linear transformations, right? So as an example, you would say that if you were going to spherical coordinates, your phi would be something like this: tan inverse root of x square plus y square over z, right? And so this is obviously not a linear transformation. On the other hand, this Lorentz transformation is a linear transformation, right? It is linear in all the variables individually. All the terms here contain only linear powers of the variables. So now whenever we have this this coordinate transformation between any two sets of coordinates, okay. So let's say my first set of coordinates is mu, my second set of coordinates is x mu prime. All right. And as a special case, these transformations will include my polar transformation and my cylindrical and spherical transformation also. Okay. For the polar case, for instance, the xy coordinate would transform, but t and z would remain constant. Here, everything would transform except for t. So what happens is that there is a matrix which becomes very important, which we use all the time, right? And this matrix is called the Jacobian of the transformation. So it doesn't matter what the transformation is, whether it's linear, non-linear, anything like that. The Jacobian can be defined for all transformations. How do we define this Jacobian? This is the definition. Okay, so Krishna, I'm going to mute you. And if you unmute yourself again without having the need to ask a question, I will have to ask you to remove yourself from the meeting, okay? Especially since your video is not turned on, I have no idea whether you're actually watching the lecture or not. So what is this? If you take this partial derivative, for instance, if you look at this, let me write this down. Let me take it like this, copy, and calculate this Jacobian for this transformation. Right. So now this matrix will contain, it's a there's yz also, but again those terms don't change, nothing happens there. So here we will have how many terms? We'll have dx prime by dx, dx prime by dt, dt prime by dx, and dt prime by dt, right? So this will be our lambda, mu prime, and mu, right? And we can read off what these elements are just by looking at this. So dx, derivative of x prime with respect to x is what? Gamma, right? So we can just read off the Jacobian elements. And what are they? Gamma minus beta gamma minus beta gamma gamma, right? So this lambda matrix Greek letter lambda. It's like an A without the step in the middle. So this is nothing but the Jacobian matrix of the coordinate transformation. Okay. All right. Any questions at this point? And by the way, is it okay if I take class till 12:15? Can somebody please give me a response to my question?
Okay, sir.
Thank you. All right. So now the next thing we can ask is what is the inverse of this transformation, right? So there must be an inverse transformation. If you can go one way, you should be able to go the other way, right? So if you have, right, if you have some matrix relation like this, you have some matrix which multiplies one vector and you get the other vector back. Then you can multiply both of these with the inverse of this matrix to give you the original vector, right? So this is the transformation one way, this is the transformation the other way around. So now what would be the inverse of this Lorentz transformation of this matrix? Anybody? There is only one small change I need to make to invert this matrix. What would that be?
Minus sign of beta changes to plus.
Right. So minus changes to plus. And why is that?
The velocity of the other frame with respect to this frame will be in the opposite direction.
Exactly. So it's just, we are just talking about the principle of relativity. That's it. So if one frame of reference, if this frame of reference is moving at with a velocity v naught in this direction, then the other frame must be moving in the, with this, as seen by O prime, this other frame will be moving in the opposite direction. All right. So I would say that x mu, right, is equal to lambda mu mu prime x mu prime. And this is the inverse of lambda mu mu prime is equal to lambda mu prime mu inverse, right? So if I want to write down the full expression, how would I do that? So x mu is equal to lambda mu mu prime x mu prime, but x mu prime can be written as lambda mu prime, let's say nu. Okay, x nu, right? So if you look at this expression, this is the transformation from the unprime to the prime coordinates, which is x mu prime. And then this is the transformation in the opposite, in the reverse direction. So what is this? This is, if you just take the, if you just multiply these two matrices, what do you get? You get the identity, you get delta mu nu. Okay. Okay, now, and also please keep in mind another important fact is that this is very important, that when I refer to this as a metric, right, these matrices, I refer to these matrices as metrics. That's because they are exactly metric. They measure distances, right? So the Minkowski metric measures a distance in 3+1 dimensions in space-time, and the Euclidean metric measures distances in what do you call it? In 3 spatial dimensions. Okay. Now, this Lorentz transformation has the property that under the Lorentz transformation, the metric interval remains invariant. This is a very important property, right? Invariance of space-time interval. Right? So if you have two space-time points, for instance, let's say you have two space-time points, x1, whose coordinates are x1 mu, and the other space-time point is x2 mu. Okay, or instead of that, maybe I don't know, x mu and y mu. And then we perform this Lorentz transformation to a different frame of reference. And the coordinates of the points in the new frame become x mu prime and y mu prime. Now we have this notion of a distance between 2 points, right? What is that notion of a distance? The norm of this is the norm squared, right? And what is this norm squared? How do I write this? I write this as minus, again, I'm setting c is equal to 1, all right? So minus x0 minus y0 squared, right? The time component squared, plus x1 minus y1 squared. So this I will just write as summation of I is equal to 1 to 3 xi minus yi. And here I can't use the summation convention. Actually, I can use the summation convention, but I'm just writing it as this way to be slightly keep things simple. And I can define the norm, the distance between the two space-time points after the transformation has taken place. So what will that be? That will be, right? Squared. So exactly the same thing, only for the prime coordinates, right? And what is the property of the Lorentz transformation? The property of the Lorentz transformation is that under the Lorentz, after the Lorentz transformation, these two are the same. So that means this norm squared will be equal to this norm squared. Under the Lorentz transformation. So this is the space-time interval, and this phase remains the same between any two events. And this is a very important point, because what it means is that when I look at, so let me try to illustrate this using a space-time diagram. Right. So this is our space-time diagram, and I'll get rid of some of the things I don't need, or maybe I'll keep them. So we have some moving observer, right? So this is the frame of reference OT. This is some O frame of reference, and then there is some observer, running out of lines, colors. There is some observer, some other system. Okay. Right. So we have somebody who's moving at some velocity v, right? And this is the observer O prime, right? So this is the time. This is the time axis of the observer O prime. It's also the trajectory of O prime as seen by O. Right? And what is the slope of this line? The slope of this line is beta is equal. M is equal to 1 by beta. Right. Now the thing is that O prime has its own light rays, right? So if I ask, what do the light rays of O prime look like? Well, the thing is that speed of light remains invariant under Lorentz transformation. Space-time intervals remain invariant, right? So one consequence of that is that the direction of light rays remains invariant. Light rays always run at 45-degree angles in all frames of reference. Right? So you might be tempted to think, for instance, that when I'm drawing these two lines here, this orange line and this orange line, you might think, well, this is just the light cone of this point, right? This is the space-time point, some space-time point. And you might think, well, this is just the light cone of this space-time point as seen by this observer O. But what I'm telling you is that this is also the light cone of the same space-time point as seen by the observer O prime. Right? Your first intuition might be, so again, let me do a little bit more editing here. Your first intuition might be to think that, well, you might think that, well, what happens to the light cone of this observer? You might think that, well, this green fellow's light cone will look like this. It will go at a 45-degree angle with respect to this guy. Right? So you might think that, well, this is what happens. Right? But this is not what happens. The light cone structure does not change as you go from one Lorentz frame to another frame. And it is a consequence of the fact. So how do we write this down mathematically? Okay. So again, let me write down the expression for the norm of any vector x. So I have some vector x. I write down the norm of this vector. How do I write it? I write it as x mu, right? Which can also be written as eta mu x mu. Right? So you can write it like this, you can write it like this, it doesn't matter. The whole point of this index notation is that the order of the terms will not make any difference, right? Because each term is just a number. This is a number, this is a number. So I can put one term before the other, it doesn't matter. So similarly, I can write this as x mu, or I can write this as x mu, eta mu, x mu. They're all the same. And again, just to go a little bit more slower and remind you all, let's say that the x mu has the values a, b, c, d. Then what happens if I lower the index? I get minus a, then b, c, d. And so if I take the inner product of these two, what do I get? I get minus a squared plus b squared plus c squared. Okay. Now, so I have this expression for the norm of the vector x as seen by O, right? As seen in the unprimed reference frame. What about as seen by O prime? What happens? Well, this will be x mu prime, right? Now you might think that, well, if I want to write the same expression, I should write it with respect to the metric, this Minkowski metric. So your first instinct might be to write this expression, and you put these prime coordinates, primes on the Minkowski metric, right? Thinking that, well, if you transform to the new frame of reference, the metric should also change in some way, right? And you are right. I mean, the metric should change in some way in general. For example, when you go from Cartesian coordinates to polar coordinates, right? What happens to your metric? Your metric goes from being 1, 1 to this, right? You get a factor of r square here. So here your metric ds square is written as dx square plus dy square. And here it becomes dr square plus r square d phi square. Right? So your expectation would be correct that this metric should change in some way. The question is, how should it change? Okay. So let's keep in mind that we have a certain requirement. What is that requirement? The invariance of the space-time interval, or the invariance of the norm of 4 vectors slash of the four-vector norm. So that means that we require that x mu norm should be equal to x mu prime. Right? This is what relativity tells us. Okay, so let me write down again this norm of x mu prime. Eta mu prime, x mu prime, x mu prime. Okay. Now, my claim is that this is equal to x mu norm, which is equal to eta mu nu x mu. Okay. So if I want to compare these expressions, let me write these coordinates in terms the prime coordinates in terms of the unprimed ones. I can do that, right, using the Lorentz transformation matrix. This is equal to lambda mu prime mu x mu. I can do this, for instance. Right. So I'm just applying my Lorentz transformation. So I take this expression and substitute over here. Okay. What do I get? The norm of my prime vector is eta mu prime, lambda mu prime mu, and now I'll collect all the lambda matrices first, and then after that I will write my x mu. Right? And again, remember, we are using the index notation. So when we write things in terms of indices, we don't need to worry about the order. Right? So if you were writing this as a matrix, let's say you were writing this as lambda x and lambda x, right? Then you couldn't just write this as lambda xx, right? I mean, that wouldn't make any sense, right? But when you express everything in terms of indices, these are just numbers, so you can move them around arbitrarily. So this is just okay, right? So this is x mu norm of x mu prime. Now this norm, this expression has to be equal according to my requirement. This expression has to be equal to this expression. Right? That's the statement, right? That the length of the vector is not going to change. And again, I'm sorry, this should be a square and a square. I forget about that. I have to be very careful. Right? Now, in these two expressions, remember that this is true for all vectors, for all four vectors. So for any four vector, this is true, right? So that means this is arbitrary, right? These x mu news, these are arbitrary. Right? And so if you have an equation of this form, you have some matrix multiplied by some vector u is equal to some matrix multiplied by some vector u. Then this means that A is equal to B, right? If this is true for all vectors u. If for all u, you have this identity, then you have A is equal to B. Only if it's true for all u, not for some particular u. Right? You can always have some particular vector for which this is true, but not for all vectors. So what does this tell me? This tells me that this object and this object, they have to be the same. So this implies that eta mu nu is equal to eta mu nu prime lambda mu prime mu lambda mu prime. Okay, and also vice versa. So if I go in the other direction, also the same thing is true with the lambda indices arranged appropriately. Okay. So in particular, if I'm working in my Cartesian coordinates, then the form of the metric remains unchanged. The components will remain unchanged. So in particular, in Cartesian coordinates, because remember, when I say t, x, y, z, these are also Cartesian coordinates, right? I could work in some other coordinates also, which are some combinations of t, x, y, z, which are not Cartesian. So in Cartesian coordinates, this is true in all frames of reference. The components of eta mu nu remain the same in all frames of reference. So your exercise is to check this by inserting form of lambda in equation for the transformation of the Minkowski metric. So we'll call this homework 1.1. Okay. So I'll stop here and I'll take any questions. And also just to mention that, well, what is this lambda, by the way? This lambda and this eta, these are all tensors. X is also a tensor, but X is a rank 1 tensor. These are rank 2 tensors. So we'll talk more about tensors. What is a tensor in the next lecture? Okay. And tensors seem like something very scary when you first encounter them. I remember that when I first learned about tensors, it took me a while to understand it. But I think that's mostly a function of either not seeing a proper explanation, or well, you just have to change your frame of thinking a little bit to understand what tensors are, and then you realize that, well, tensors are just about changing frames. So it's not surprising that you have to change your frame of thinking to understand tensors. That's a funny joke. Nobody caught that. Never mind. All right. So I'll stop and see if you guys have any questions.
Sir, am I audible?
Yes, you are.
Sir, in Cartesian coordinates, suppose we changed y prime and z prime, still the Minkowski metric would be invariant.
What do you mean by we changed y prime, z prime? I don't...
In this, we assume that x and x prime were moving parallel, so y and z coordinates didn't change in Lorentz. So if they changed, we assume some kind of transformation that it changed.
Sure.
Then still Minkowski metric would be invariant in Cartesian coordinates.
Yes. Yes, yes, it would be. So, so the thing is, see, Lorentz transformations, this what we call the group of Lorentz transformations. Okay. It contains these elements, right? These elements are called boosts when you change the relative velocity. Okay. But you have these rotations also, right? So there are two kinds of rotations. One is your regular rotations between x, y, z in terms of cosines and sines. And then you have your hyperbolic rotations between tx and ty and tz. These are your hyperbolic rotations. Okay. So now a Lorentz transformation in general is some arbitrary combination of these spatial rotations and boosts. Boost is this hyperbolic rotation whenever you have tx, ty, tz. Okay, so a Lorentz transformation, I've written it down here in this way. This is a very specific case. Here you could have some rotation in the yz plane. So instead of identity, here I could have cosine minus sine, sine cosine, right? That's fine. This condition will still be obeyed. This condition will be true regardless. And in particular, this expression will continue to hold. Okay. Now, Lorentz transformations do not include general coordinate transformations. For instance, if I go from Cartesian coordinates to polar coordinates, right? Let's say I'm in the YZ plane. In this YZ plane, I perform a change of coordinates from YZ to R theta. Now that will not be described by a Lorentz transformation. That is a general coordinate transformation. That is not part of the Lorentz transformation. So under that transformation, the metric will not change. The metric components will change. Okay. So this is true for Lorentz transformations only, not for arbitrary coordinate transformations. Anything else? Okay.